Okay guys, in the previous class we discussed about the complete state controllability and the output controllability. So if you remember that we had complete state controllability, that's right, we had to check this controllability matrix B, AB, A square B until A to the power of n minus 1 B for the nth order system. And then we had output, if you remember, controllability. So we had to check this controllability matrix. CB multiplying from the left, CAB, CA square B, remember, until CAN minus 1B and the D. For what? For the LTI system, x dot is equal to AX plus BU, and the Y output is equal to CX plus DU. That's right. But before going to observability, let me do a trivial example of what I'm talking about. Example is this trivial pendulum. You have seen this a million times in undergraduate control and vibration and even dynamics in robotics, ML and the angular theta. And I apply a control torque tau that I name it U, and I skip that I how drive. Let me see if it's recording. Come on. Yep. So skip how to drive the equation of the motion, because you know this theta double dot is G over L sine of theta is equal to tau or U. That's right. After linearization around the equilibrium point, I taught using this Taylor series expansion, you get this LTI system theta double dot plus G over L theta is equal to U. Obviously it's a function of time, right? So now I'm defining x1 as theta state variables and x2, and now you know it, is theta dot. So from here you get x dot 1 is theta dot, which is x2, and x dot 2 is theta double dot, that from here you get minus G over L theta. Theta is x1 plus U. Now if you remember the vibration course, we were naming this what? Yes, natural frequency square. Okay, so your state space LTI system in the state space form of that is x dot 2 is equal to minus omega n square x1 plus U. So what I want to do, I want to make it in this form exactly. So you can write as this, that's right. You can write as x dot 1, x dot 2. Now AX, x1, x2. Here you have x1 in this line, you have no x1, it's going to be 0. You have 1 x2 is 1. x2 you have here 0. Sorry, x2 you have no x2 here 0, and here minus omega n square plus BU, because it's a single input single output, so we have 0 and 1 U. Here we go. Understand? So this is your A matrix. This is your A matrix. Matrix A. This is your B matrix or vector B. So going to the next page. Going to the next page. Having A as 0, 1 and minus omega n square and 0, and B as 0 and 1, right, from the previous page. Look at here. Assuming that the length of the pendulum is 1 and the g assuming is 10 meter per second square, so your matrix A becomes 0, 1, and the Lagrange score is G over L, 10 minus 10, that's right, minus 10, and 0. And matrix B gonna be 0, 1. If I want to examine the controllability, state controllability of this matrix, complete state controllability of this matrix, we have to check this controllability matrix B and AB, because the second order system, n is 2 second order system, so n minus 1 is 1. That's right, look at here guys, the power of an minus 1. So if you put it here, it is 0, 1, B and A and B. Look at here, A in B, 2 by 2 and 2 by 1. So gonna be 0, 1 and 0, 1, 0. Here we go. That's right. 0, 1, 0, 0. So the rank of this matrix, if you use MATLAB as I told you, rank of this matrix, say M, controllability matrix, rank of this matrix 100% gonna be 2. So, and also its determinant is not 0 for this square matrix, right? So it's not singular. So the states of this pendulum are completely controllable. Okay, as I told you previously in the previous class. Let me go to the MATLAB because I want to teach you the command. Okay. Okay, so see, if this is your 0, 1, 1, 0, that's right, rank of 0, 1 and 1, 0. All right. Yeah, 0, 1, 1, 0. Oh, sorry, 0, 0, 1 or 1, 0. That's right. Rank of this is 2. So your system is completely what? Controllable. Understand? So, but if your order is high order, you can say my matrix A is 0, 1, 0, 1, and 1, 0. That's right. Oops. Right. And your B is 0 and 1. That's right. In MATLAB, it's very easy after graduation. Double check. 0, 1, 0. We have a say I think this is the command. Controllability matrix. You can have it by this command. Yeah, exactly this. Controllability matrix. You give A and B. This gives you controllability matrix that we already had. That's right. This is controllability matrix that we already had. Oh, guys, note. I'm stupid. This is 0, 1 minus 10, 1. Your A's. Your A is this, and your B is that. So controllability matrix is gonna be again this. So on the rank of this is 2. So this command, ctrb, by giving the matrix A and matrix B, gives you the controllability matrix, and you can name it whatever you want. You can say M, whatever. So M is this. So rank of M is what? 2. Understand? So this is the MATLAB part for the controllability. So okay, so we continue. Hold on. So okay, so let's continue. So in x dot is equal to ax for the LTI system plus bu, and the y is equal to cx plus du, you have to know some trivial rules, which is having du in y output equation, y equation means here, okay, always helps establish output control ability. You have to know this, okay? So another things that you have to know is that, which is obvious, if a sub system of a given system is physically recording, is physically disconnected from what? I'm changing the color to emphasize. From the input, means control input, U, the system is uncontrollable. Okay. Now let's go after this to observability. Okay. Suppose you have this system, guys. X dot is equal to AX, is LTI system. Y is equal to output is CX, and this is unforced system. There is no control input. That's right. Where X is a state vector, as you know. That's right. N vector. Okay. Y is output vector, M vector. Okay. A again is N by N matrix, and the C is M by N matrix. Okay. So that's it. Having this system, the system the system is said to be completely observable if every state at initial time t0 can be determined from the, I'm changing the color, observation of output y of t over a limited time t between t0 and t1. The concept of observability is useful in solving the problem of reconstructing unmeasurable state variables from measurable variables. Okay, clear? So variables in minimum lengths of time. Okay, so simply observability help us unknown state variables in limited time between t0 and t1 limited time, measurable variables. That's right, measurable variables. If we can do that, we can estimate the unknown state variables. So this is observability. So going to its mathematics, like the controllability, we assume t0 without loss of generality is 0. Okay. So, and sometimes some state variables are not accessible from direct measurements. Like what? Can you guess it? And hence we need to, I'm changing the color, estimate the unmeasurable, it's too bad, unmeasurable state variables to make control signal. So in the controllability, we are checking that if the system is completely state controllable or output controllable. But in observability, we gonna estimate the state variables that we cannot measure it by sensors or whatever. Okay. If a system is completely observable, okay, such estimates are possible. So again, in controllability, we are checking that, for example, x1 and x2 can be controlled by a control input, but in observability, we gonna estimate x1 and x2 if they are not accessible to measure. Okay, understand? So now let us go to its mathematics. So in the controllability, we had to check the controllability matrix b a squared b a n minus 1b. Or output controllability cb ca ca2b and forward. Now for this LTI system, x dot is equal to ax plus bu, the y is equal to cx plus du, the LTI system. We know that we derive together that its solution x of t was matrix exponential EAT x at time 0 plus 0 to t. Remember, you have in notes EA t minus tau, that's right, B matrix, U tau, not the Utah city, this Utah, and D tau, that's right. So by putting x here, you get the y is what? CEAT multiplying with C. X at time 0 initial condition, I said t not is 0, plus C in 0 to t E A t minus tau B U tau D tau plus du. So this is your output, that's right, the output vector, that's right. Understand? So in this, what we want to do, observability, is that by observing the output, and these are known matrices, that's right, known matrices, these are known, but this is unknown, the state variable is unknown, so we want to, these are unknowns, we want to estimate this, okay, in observability. Understand? These are unknown states that we want to estimate. Okay, so mathematically writing, so on that equation that you saw on the previous page, in this equation, output vector. Come on, this. Here, matrices A, B, C, and D are known, and U of t, the control signal, is also known. Huh? No. But the state variables are not measurable, so we want to estimate those. Okay. Hence, it suffices to consider the system of x dot is equal to ax and y is equal to cx, because bu are known, so, and the du is known, so only the involving the state variables that we want to estimate are these. That's right. So having that, now we have to consider the condition for, as we did for the controllability, for a complete observability of systems. Okay, guys, remember that in the beginning of this semester, when I said A is equal to AX, its solution was what? Its solution was E matrix exponential at time 0. Remember, go to notes, you will see it. I taught you this. Now putting this inside here, so the Y output gonna be C E A T at X at 0. Yes or no? That's right. And also you had in your notes, and we had matrix exponential, remember, was sum of k from 1 to n minus 1 alpha k of t as a function of time, a to the power of k. Remember that we got from Sylvester relation. So by replacing this here, we get that we derive this together. You have it in notes. Y is equal to sum of k from 0 to n minus 1 alpha k of t, that's right, c, we are just replacing here, c e a t, that's right, x at time this. Understand? So now give k0, k1, k2, k3. So y, if I expand, this gonna be what? Look at here, guys. K0 gonna be alpha naught of t. Okay, c t0, so this gonna be unity matrix, identity matrix. That's right. Oh, it's not like that. Okay, let's replace it here. Okay, so, and what the hell I'm doing, guys, I'm sorry. Okay, I just replaced this here we go. Okay, so k0 gonna be alpha naught t, c a to the power of 0 gonna be identity matrix in x naught, that's right, x at time 0, sorry. K is equal to 1 gonna be alpha 1 of t, again c a in x at time 0, plus finally alpha n minus 1 of t, c a n minus 1 x at time 0. Bingo. That's right. Here we go. Now I can rewrite this. I I can write this write this as y of t is equal to, for example, like this: alpha naught at x x this, alpha 1 x naught, and until alpha n minus 1 at x naught. That's right. So here they're gonna have c ca square until ca to the power of n minus 1. Here we go. That's right. 1 in n minus 1, and now n minus 1, n minus 1 and n minus 1 in 1. So it's going to be 1 by 1. That's right. You can write like this. So having this, it says x at this value is determined because, as we said previously, this is known, C known, A known. That's right. And obviously alpha known. Okay, is determined from observation at this limited time. Understand? Clear? So the name of this matrix is ca square ca n minus 1 is observability matrix. Observability matrix. If you want to know that the states of a given system are observable, or you can estimate them based on the observation of the output, you have to check the rank of this matrix, guys. So you have to say rank of this. Oh, what's happening? You have to say rank of this matrix. Rank of this matrix is equal to n. Your system is completely state observable. Understand? So this is that. Okay, so on the other hand, because you're going to find these state variables, you have to have the inverse of this. That's right. You have to have inverse of this. So now, so if I summarize in the complete state controllability, you have to check the rank of this matrix: B, A, B, A square B, A n minus 1B. If you want to check the complete state observability means you can estimate the unknown state variables. If you cannot measure them directly, you have to check the rank of this matrix. Rank of this matrix for controllability, and the rank of this matrix ca minus 1, right? For which system? For this LTI system. X dot is equal to ax plus bu, the y is equal to cx plus du, for which is, this is n by 1 vector, so it's gonna be, this must For completeness, this must be equal to n. The rank of this matrix must be equal to n. Understand? So let us do some example for observability. Example. Suppose you have this second order system, LTI system. X dot x2 is equal to 1, 2, minus 3 and 4, x1 and x2 plus bu, and the y, because you are talking about observability, the output is 1 and 1, x1 and x2. So it means that in the output we want to see both, for example, the angle of the pendulum and the velocity of the pendulum. Understand? So I want to examine first state controllability. So we have to make B and the AB. AB, this is your A, this is your B, and this is your C. AB, so B is 0 and 2, and the AB gonna be 0, 4, and 0, 8. Right? So this is controllability matrix. This is controllability matrix. So we have to find now rank of this. You have to find the rank of this. This is score matrix. The easiest way for the score matrix is that to find the determinant, which determinant of this is non-zero. It is how much? It is minus 8. Right? Huh? Or you can go to the MATLAB, or you can go to the MATLAB 0428. Got here. Rank of 0, 2, 0, 2, 0, 4, and 2, 8 is 2, obviously. So the system is state controllable. Understand? So this is one point. So now if I go to let me go to the next page. Hold on, guys. So if I go to the state state observability, so we have to make this matrix, guys. C, and the second order system, CA. So your C is what? How much? Your C is 1 and 1. CA gonna be 1 in 1, right? Multiplied by 1, 2, your A is minus 3 and 4. This is 1 by 2, 2 by 2. This is gonna be 1 by 2, obviously. Right? It's gonna be 1 by 2 to 1 by 2, obviously. It's gonna be this 1 minus 3 minus 2, 1 plus 4, 6. It's gonna be minus 2 and 6. But you can do this. I'm saying observability matrix. You can do like this. There's a command in MATLAB after graduation, not for the example, for the exam. You can say your C is how much? 1 and 1, and your A was how much? 1, 2, minus 3 and 4. That's right. So observe of A and C, if I'm not wrong. This is the command. No, observe. If I'm not wrong. Yeah, it is. Observe. This is the command. OBSV, observability command. You give a matrix and the C vector, it's gonna give you observability matrix. So obviously the rank of the answer is 2. Or if you do that, say determinant, I'm not sure it's working or not, let me try it. Determinant is 8. So obviously this is state observable, means that you can estimate the state of the system. Understand? 1 1 minus 2 6 to get here. 1 1 minus 2 6. Understand? Clear? So this is another things that you have to know. So this is for state space. So when it comes to, if I give a transfer function, you have to know this rule. The rule is the system is completely state controllable and observable, means we can estimate the state variables if the transfer function has no cancellation, as we did for the controllability. Understand? So now, after knowing that how we can judge the system is controllable or system is observable, the question is that how we estimate and how we design controller. Okay, so these are the main topics of this course. Until this part was the introduction about the controllability of state variables, and observability means estimating the state variables. But the question is that how we do that. Okay, so I'm going to do it by the next class.